Morning, everyone, and welcome. Quick reminder, this session, as with all sessions, are being recorded. We are in the Z Performance and Capacity stream, and this is session 5J, WLM Effective Transaction Management with Peter and Rico. I'll ask if you have any questions, feel free to put them into the chat. And Peter or I will call them out so that he can respond to them. And please don't forget to fill out your session feedback at the end. With all that said, welcome, Peter, and I'll let you take the floor.
Hey, thank you, Donna. I really appreciate it. Good afternoon, everybody, or good morning if you're in the United States, or I guess good evening if you're in Asia someplace. Yeah, my name is Peter Enrico from Enterprise Performance Strategies. And this is actually the first time I'm presenting this particular presentation. I present a version of this in my class, but the UK GSE was looking for a different type of topic. I said, this is an interesting topic. And I think it's very interesting. So hopefully you'll enjoy it. As Donna mentioned, or maybe I would have mentioned, feel free to ask questions. And I also want to mention that this is actually quite a long presentation, and I will keep it within the 45 minutes. And just know that when you get the handout, there's more slides in the handout than I might be presenting. Just want to point that out. Just real quickly, just 2 minutes, not even less than 2 minutes. Just real quickly, who I am. I'm Peter Enrico of Enterprise Performance Strategies, and what we do is ZOS performance. So we have our SMF data reporting, decollect all types of data reporting service called Pivotor. So if you're interested in having your performance data reported on, or accounting, or whatever you want, it's a pretty great service. We also do education and instruction, and as you can imagine, we teach workshops which are coming up, and we also do all the conferences and whatnot. We do something called Performance War Room. So if you're ever interested in having us come in for a short, concise period of time to find as many performance recommendations as possible, that's one of the things we do with our Performance War Rooms. And then we have MSU reduction exercises that we take part in. So if you're ever interested in that, that's something else we do. Real quickly, these are our classes. Actually, I just realized the April class dates are wrong, but the performance class for WLM is coming up in second week of May, not the first week of May. We do a performance class for parallel sysplex and one for basic tuning, which is I/O, processor, and storage. So certainly consider those. And the other thing I just want to mention real quickly is just about every 2 weeks, we give a half an hour performance webinar on Wednesdays. These are free. You just sign up for them. You get notified. And every 2 weeks we do this. It's about a half an hour, maybe sometimes longer, sometimes shorter, but a half an hour. And then we do a Q&A afterwards of any topic you want to do. We've been doing these now for about 4 to 5 years. So if you have not been participating in these performance webinars, certainly consider yourself, just go to our website, sign up. The ones listed here, the ones coming up, I guess the ones with the red bullets are the ones we've done already. So these are the ones coming up. So I think next week we're doing CPU critical. So certainly take a look at them. And finally, yeah, that's it. So let's talk about transactions. So as you know, on the ZOS platform, we have a variety of workloads. And one of the presentations I think I gave at the previous GSE was different types of address spaces and how to look at address spaces. And what I wanted to do this presentation was to take a look at actual transactions and what is a transaction. And the reason you need to understand what a transaction is from a workload manager perspective, that's also a key point. Is from a workload manager perspective, is we want to be able to set an effective goal. We want to sometimes say to ourselves, hey, is this thing eligible for a multiple period service class? And we just kind of basically want to look at what the measurements are, or when we look at our SMF measurements, where, what is actually being accumulated. And that's what this is really all about. Because when you think about it, let's say I have a transaction, a TSO transaction that you want to get a quarter-second goal for. Then you have a DDF transaction you want a quarter-second goal. Then you have an OMVS transaction you want a quarter-second goal. Then you have a CICS transaction that you want a quarter-second goal. And the question then becomes, well, if they all want a quarter-second goal, why not put them into one big service class and let them all be managed together? And the reason we don't do that is because they really are managed differently by workload manager. And that's kind of what this presentation is about saying this is what a TSO transaction is versus, let's say, a USS transaction. So hopefully you'll learn something and you'll see kind of what what considerations you need to take into account when setting a goal and when setting, determining if you want multiple periods. And that's what we're really talking about here. So as all of you know, this is the first part I'm going to go through quickly because you all know this already. As you know, all work coming into the system gets classified through a series of classification rules. You can kind of see my diagram here where we have our KICS classification rules and DDF for the DDF transactions and OMVS for our forked children. And eventually they get associated with a service class and report class and yada, yada, yada. That's all standard stuff. But what actually is being classified is what we're interested in understanding here. Now, understand that when you classify work in Workload Manager, we're talking about transactions here. So although you heard me say the word address spaces before, yes, address spaces can be transactions, but that's a different topic, the type of address space. What we're actually talking about here is what actually is being classified. Now, you can see here on this particular diagram that I have three different boxes. And the reason these boxes are separated is that we have different types of transactions at the very high level broad category. On the left here, where it says APPC and JES and USS and TSO, what we're classifying there is address spaces. So you have your TSO classification, we're going to be classifying address spaces. As opposed to on the right here, where you see it says component broker and DDF and all that, we're actually classifying enclaves. And then down below here, we're classifying something that's neither an address space or an enclave, and we're really talking about our CICS and IMS transactions. So that's kind of the topic what we're talking about here. And again, real quickly, again, you probably all know this. When I say I'm classifying address spaces, the classification rules we're talking about are the ASCH, the JES, the OMVS, the STC, and TSO classification rules. We classify transactions. When you go to the CB or DDF or TSCP or iWeb classification rules, you're actually classifying enclaves. And then down below for IMS and CICS is for those types of transactions. I'm not going to go through it all here. I just listed here for completeness. I do want to point out that from an address space point of view, when you classify, most of you are interested in the JES, which of course is our batch, our OMVS, which is forked children, our STCs, which is started tasks, and TSO, which is TSO users. Not a lot of people use APPC, which is the ASCH these days. When we talk about managing things or classifying things at the enclave level, the most popular ones are CB if you're using WebSphere, DDF for DDF transactions, NetV for the NetView, which many of you have, TCP for IPsec, and iWeb. That's mostly what you're going to be doing. You see other classification rules for EWLM and DB2, which is your remote parallel queries, which aren't even supported anymore. LSFM, MQ for MQ series workflow, and SOM. Nobody really uses these. And in fact, one of my recommendations is when you go to your classification rules, just delete these subsystems. You're not going to be using them. Why clutter up the service definition with this junk? And then you have IMS and KICS. Okay, but we all know that to achieve optimal performance, we need to set the proper goals. And what we want to understand is, why do we sometimes set response time goals and other times we set velocity goals? Or for some workloads, we can set either response time or velocity goals. The other thing is in terms of multiple periods, why are certain transactions eligible for multiple periods and other transactions are not eligible for multiple periods? And when would you use a multiple period? And then there are also things like feeder effects where we always want to make sure that if we have our transactions, we want to make sure that the feeder effect, meaning if a particular address space or transaction doesn't do well, then this transaction won't do well. So we want to make sure that we actually are able to control the feeder effects to make sure that anything that's feeding me is actually performing better than me because that way it's feeding me. And one of my rules of thumb I always say is, to answer these questions, one of the rules of thumb I always ask that my customers to answer is, if the life of the address space is different than the life of the transaction, then it means that both response time and velocity goals are possible for that transaction. And it also means that that transaction is eligible to be put into a multiple period service class. Now, you might not understand what I just said, but what I'm trying to get you to understand is there are certain situations where a multiple period service class makes sense and certain situations where it doesn't. The same thing with response time goals versus velocity goals. So the rule of thumb is I always look to see if the life of the address space is different than the life of the transaction. And you'll see what I mean in a moment. So what I do, and this is just me, this is You're never going to find this in a workload manager manual or anything like that. What I think of is when I look at transactions, I, in my mind, group the transactions into four categories. And each of those four categories helps me understand how we are going to classify the transactions and what kind of goal and things we give to the transactions. The first group is what I call undistinguished transactions, which is just what we think of as typical transactions. Second group is Group B, which is your KICS and IMS transactions. And the reason I separated those out is because they are managed completely differently than Group A, for example, which means we have to give them a different consideration when setting a goal. Then you have Group C, which is our enclave transactions. And the reason I separated those out is that enclave transactions are given different goals and are measured differently than either CICS or IMS transactions or what I call undistinguished transactions. And Group D is sort of a weird category, but it's probably very popular for most of you, is what I call morphed transactions. And a morphed transaction is one in which it starts out as one type of transaction and then becomes another type of transaction and maybe even becomes another transaction. So the example might be, I have a KICS transaction that becomes a DDF transaction that becomes another CICS transaction or whatever. That's what we're talking about here. So let's get kind of into this. And so what we're talking about here is first undistinguished transactions. And this is probably what we think of as typical transactions. We're talking about non-KICS or non-IMS response time goal work. We're not talking about enclaves here. We're not talking about morph transaction. We're talking about what we think of as typical transactions that when we think about ZOS or ZOS on a regular basis. This is our TSO, our batch, our OMVS. And in this particular case, we classify these transactions towards their goals, towards their particular subsystems. And we always have to make sure that we take into account when setting those goals, what those transactions are actually doing. So for example, the simplest case is a TSO transaction. Now, I had mentioned earlier that when we set a goal for the transactions, what's important to understand is the life of the transaction different than the life of the address space? I think about that. So when we classify something with the TSO classification rules, what we're actually classifying is the address space. So what's happening is we log in, the address space starts up, and the address space is a long-running address space, right? At night, that's the life of the address space. But as you know probably already, is that we're able to set um, uh, response time goals for the transaction. So if the life of the address space is a very long address space, then how do we set response time goals? And that's because the life of the transaction that we're measuring is different than the life of the address space. When you hit enter at TSO, that's what WLM is considering. The address space is already classified. It's the transactions that we're trying to control. And that's why we have to understand that that's what makes response time goals possible. Because if we looked at the life of the address space, it would be an 8-hour response time, but we're able to understand the individual transactions. And that's why we have response time goals. But we're also able to measure the CPU time of those transactions. So we can say, oh, look, this transaction used up, a millisecond of CPU time. This other transaction used up a second of CPU time. And because of that, that's why we're able to look at multiple periods. So for example, with TSO, you have a typical, on the left-hand side here, you have a typical TSO address space. We have a command processor. This is what I'm saying. The life of the address space is the big address space. But every time we, quote unquote, fork into a different TCB for a command processor, we understand that transaction. So we know that that might be a short response time goal. We know the CPU time, which means we could choose to put it into a multiple period service class, depending upon how much CPU time the transaction is consuming. But then you take B, for example, where we have to take this into consideration. If my TSO users are actually entering DB2 queries, the DB2 query is actually running in the DB2 address space, but the portion of the query in the DB2 address space is an extension of the TSO user. So though the transaction is performing and running in the DB2 address space, the CPU time of that transaction in the DB2 is actually accumulated back to TSO. The dispatch and priority of the query in DB2 is that of TSO. And that's why we can, certainly make it into we're able to measure that CPU time. So we're able to know the full DB2, the TSO transaction. And so if I look at the 72 record or the SMF 30 record for TSO, it's going to include all that DB2 time. But in this particular case, I might have to take into account the longer CPU, longer response time that maybe, it's not just the command processor, but maybe now I have a longer response time. And that's why we have to kind of look at things like multiple periods and see if we want to put it into a longer response time period, for example, for a goal. And the same thing is true up above, where if I have a TSO user calling a stored procedure, that stored procedure is running in another address space called the WLM stored procedure address space, which is probably accumulating, doing DB2 queries in the DB2 address space. Just understand that the CPU time of the DB2 query, the CPU time of the stored procedure is accumulated back to the TSO transaction and back to the TSO address space, not to DB2 and not to the WLM stored procedure address space. So again, the reason that's important is that if we're going to set a goal for TSO and we know those TSO transactions are calling stored procedures, we might want to make it into a multiple period service class where we have a longer response time objective for that type of transaction. And we also know that all that CPU time is accumulated back to TSO. So that's why we have to take that duration into account when we're doing multiple periods. So that's kind of what we're going on here. Understand what a transaction is. So a TSO transaction on the left here might have a very short response time goal, where here with the stored procedure might have a longer response time goal and might want to be put into a lower period. I'm not going to present these slides, just talking about where the response times and CPU times are accumulated, and I do that for all the different examples. Now here's another example for a started task. What's a started task transaction? Well, in this particular case, the transaction is the address space itself. So remember I said we have to take into account, are we running long-running address spaces, and are we able to distinguish the life of the address space from the life of the transaction? In the case of a started task, we can't make that distinguish. We can't distinguish that. So in other words, let's say we start the started task at, let's say, midnight when the system is IPL'd, and let's say that started task runs for 24 hours. That's the transaction. There is no concept of individual transactions for that address space. Think of your monitors. Think of, a CICS address space. It doesn't really matter. The point is the address space is a very long-running address space, but we're not able to understand that we understand that the transaction itself is that of the address space. If I bring down a started task after 13 hours, that response time for that transaction is going to be 13 hours. The CPU time for that transaction is going to be that which is accumulated in 13 hours. So understand that from a started task point of view, the life of the address space is the life of the transaction, and because of that, we can't give a response time goal for a started task. We can't put them into multiple period service classes because think about it: you'd start the started task. It accumulates CPU time. It's going to go to the last period and stay there forever. And that's not what multiple periods are all about. So again, that's an example. And again, all the CPU times accumulate back to the address space, and it's all going to be on the subsequent slides how that's all done. Now take an example of batch. The question becomes, is batch a long-running address space or is batch a short-running address space? Now, it's unfortunate that I'm not in front of you right now that I can have you answer that question dynamically and look at your eyes and all that kind of stuff. But let me ask you this question. Think to yourself, is batch a long-running address space or a short-running address space? Because remember, if it's a long-running address space, then are we able to distinguish the transactions away from the address space, or is it a short-running address space? A long-running address space where we're not able to distinguish the transaction from the address space. So I might not be able to see your faces, but most people say, well, batch can be a long-running address space or it could be a short-running address space, because if it's an IEFBR 14, then it's short-running, but if it's a big batch job that runs for 10 hours, then it's a long-running address space. And the answer to that question is no. It's either long-running or short-running. It's not either or. And in this particular case, a batch address space is a very long-running address space always. And why is that? It's because a batch address space is an initiator. So an initiator usually start the initiator is up for many hours, and then when you submit the batch job, that batch job takes on the initiator, and that's the start of the batch transaction. So now we know for batch, we're able to distinguish the life of the address space away from the life of the transaction. The life of the address space is the initiator. Okay, that's kind of interesting, but the transaction is that of the batch job that uses the initiator. I mean, think about it. Why do you think we have initiators? I always ask this question in my classes. Think about it. One day, an IBM came in and said, we're going to create these things called initiators. Why is that? Why do we care about initiators? And most people say, well, we want to make sure we're able to control the job because job class A needs this many initiators and job class B needs this many initiators. No, that's not why we have initiators. That just happens to be a byproduct of all the junk that initiators created. The reason you have initiators is so that the creation and deletion of an address space, which is very, very expensive, you can't do that for your batch workloads. You can't say, oh, look, I'm gonna create an address space when I want to run an IEFBR 14. Or I'm going to create an address space when I want to run this dump. Or I'm going to create an address space when I want to run these 1,000 batch jobs. That is extraordinarily expensive to create those address spaces. So the operating system came up with is an idea that says, why don't we create a pool of address spaces, leave those address spaces out there so we've gone through the expense of creating the address space, and then let the batch jobs take over these initiators, and that's the transaction. In a lot of ways, it's almost like what we did with TSO. We create the address space, but then the individual transactions are distinguished from the address space. The point being is that a batch job is eligible for multiple periods, and a batch job is eligible for response time goals as well as velocity goals, because we can know that this particular batch job ran for a half a second and this other batch job ran for 10 hours. Because we know that, that's why we can give these different types of goals to these different types of transactions. And again, this is just the CPU times and things like that. Another type of transaction we're always interested in is Unix system services. When you classify OMVS work, what you're actually classifying is a forked child. And that's a commonly misunderstood concept by a lot of people. Typically, the originator is already classified. It's the forked child that we need to have classified. So for example, if you look on the lower right here, a lower left here, we have a parent process, right? So in Unix in general, you have a parent, and every time you hit enter, every time you enter a command, you fork a child. So what fork exec is all about is fork exec is saying, I have an address space and I want to run something in a separate environment away from my address space. Because if that thing I want to run fails and it brings down that process or whatever you want to call it, I don't want it to affect me. So I'm a parent and I want to run something in an independent address space or process, what they call a process, than me. So that way, if it fails, I'm still protected. So what Unix System Services does, or Unix in general, has nothing to do with Unix System Services, but what Unix does is what's called a fork exec. And what fork exec says, I'm a parent, I'm going to do a fork, right? So you're running a program, it does a fork. What a fork does is says to the operating system, create another environment or get whatever I need to run this child process so that I can actually run a program independent of my address space. Then you have what's called an exec, which says, this is the program I want to run. So fork, I needed a different environment, and exec says, this is the program I want to run. So at this point, what I usually ask my students is, what other workload on ZOS does almost exactly the same thing as a fork exec? And they'll say, well, maybe this, maybe that, maybe this. And typically they don't answer the right answer. What a fork exec is like in a Unix environment, or in Unix system services in particular, in this example, it's almost identical to batch. Think about it. I'm a TSO user. I want to run a program independent of my address space. So what I do is I have a batch job and I submit it. It's kind of like a fork. And what's one of the very first what's one of the very first cards in my JCL? An exec to say, this is the program I want to run. That's exactly what a fork exec is. So in this case, a parent forking and execing a child is almost identical to batch. And a batch, that means that the life of the address space is different than the life of the transaction. And that's why for Unix system services, we can have response time goals, we can have velocity goals, we can have multiple periods, because we have this independent address space. Now, in the world of batch, we have something called initiators, and you control the number of initiators, and we know that whole thing with Jez and all that kind of stuff. In the world of Unix system services, You don't have initiators. What you have are BPX AS address spaces. Basically, what they did for Unix system services, well, first of all, yeah, basically what they did for Unix system services is they said, look, creating and deleting an address space is very expensive. So let's create a pool of address spaces. Let's call them BPX AS and keep that pool out there so that every time a new child needs to be created, I just take a pre-created address space and make it into the child, which is exactly what Batch does with initiators. Only with Unix system services, they were smarter and they didn't give people the option of controlling the number of BPXAS address spaces the way they did for initiators. So that's what that's all about here. So because we're able to distinguish the life of the address space from the life of the transaction, that's why we're able to do that. Now, just one side note here. If you look at the right-hand side here, you have a fork exec within a different TCB within the address space. So I just want to point out something real fast. Remember that Unix System Services is not Unix. What it is it's the ZOS operating system providing Unix system services so that you can run Unix-oriented programs and to be classified. What's the word I'm looking for? Not classified, certified as a Unix operating system. You have to adhere to the Unix system services. So by default, the way Unix works is I have a parent, the child's in a completely different address space or process. So on ZOS, what they do is they use address spaces to represent processes, where on Unix, it's just a much lighter thing. And because that's very expensive, we don't always want to do that, but that's what has to be done through the standards. You have to do it on the left-hand side here. But then the ZOS developer said, we're going to be a little clever here. By default, we're going to make it work the way it runs on the left of the screen. But then we're going to give the users an option called share AS equals yes. And if you optionally turn that on, then if you can fork within the same address space, just another TCB, that happens. And in this particular case, you can still set a response time goal, but, and even multiple period goal, but, it's a much lighter way of doing the service. So I don't know if that makes sense to anybody, but just know that that's different ways of running Unix system services. Okay. So that's just an example of what I would call the boring transactions. So you can see why we have, response time goals, velocity goals, and durations for those. So let's talk about CICS and IMS transaction goals. Now, what we're talking about here is not the CICS and IMS address spaces. That's a different discussion. What I'm trying to classify here are the transactions flowing through these address spaces that actually are what we want to control with response time goals. So the way it works on ZOS is when you have an IMS or CICS transaction, they're only eligible to run with response time goals. And the reason we're going to see in a moment for that is that we're not able to distinguish the CPU time. We're not, how do you say? We're going to say that it doesn't run in enclaves, and you have no ability to control one transaction away from the address space relative to another transaction in that same address space. So I'll show you in a moment. I guess I kind of jumped ahead. But what I'm trying to show here is I have a transaction, let's say CICS, that flows through a TOR, AOR, FOR combination. Or here's an example where it's TOR, AOR, DB2. That's what we're talking about here. I could have shown you the same thing for CICS. But when we look at it from a transactional point of view, what happens is, let's say for CICS, when it enters the TOR, it gets classified. And while it's in the TOR's address space, it's going to run at the TOR's dispatching priority. The CPU time is going to be accumulated back to the TOR. When it goes to the AOR, it's going to run at the AOR's dispatching priority, and the CPU time is accumulated back to the AOR. And the same thing for the FOR. The only sort of variation of this is when the AOR calls DB2, although the query might run in DB2, the CPU time is accumulated back to the AOR. The point being is eventually when you look at the CPU time of these address spaces, it's going to include the CPU time that was accumulated while those transactions were running in those address spaces. But we're not going to get a type 30 record, for example, that shows us how much CPU time the different transactions consumed. Yeah, for CICS, we can look at that, and we can look at the 110 records, for example, and that's used instead. It's just not done at the 30 record. But the point I'm just trying to bring out is in this particular case, we don't, by nature, WLM doesn't know the CPU time of the individual transactions away from the other transactions. And because of this, we're only able to give response time goals to CICS and IMS transactions. And that is because, first of all, from a velocity goal point of view, we need to be able to sample the transactions and using and delay states. But again, we don't know that because all we know is that the transaction is starting, the transaction's ending, and we know the address space it's accumulated in, but we don't know the CPU time away from the address space. It's part of the address space's CPU time. So we can only use response time goals. We can't use velocity goals. And the same thing is true for multiple periods. You can't use multiple periods for CICS and IMS because we're not distinguishing the life of the address space away from the life of the transaction. They're one and the same. So that's what I want to point out here. So when you, by the way, when you set these transaction goals, you have to take into account, hey, where is it flowing to? And in this particular case, where is the CPU time flowing to and things like that. Oops. Here's just an example of IMS or CICS calling a stored procedure address space. Just wanted to point out from a transactional point of view, the response time of the transaction is the entire flow. That's the response time. But again, because we're not able to distinguish the life of the address space from the transaction, the CPU time in the TOR accumulated by this transaction is accumulated back to the TOR. The CPU time in the AOR by this transaction is accumulated back to the AOR at the AOR's dispatching priority. But from a stored procedure point of view, issuing a DB2 query, these run in what we call dependent enclaves. So as a result, the CPU time of these transactions are accumulated back to the AOR, and the dispatching priority of the transaction, not the address spaces, of the transaction are that of the AOR. Right? Just want to point that out. So we need to take that into consideration when we start looking at CPU time accumulated by the AOR. We have to take that into consideration. We start looking at response times that these transactions call stored procedures. And again, this is just the information. The third type of transaction is what I call enclave transactions. And what we're talking about here is when we're able to run the transaction in an enclave. And as you probably know, enclaves, you can distinguish the life of the address space away from the life of the transaction. You're able to accumulate the CPU time to the enclave, to the transaction, away from the address space. And I'll show you that example in a moment. So here's an example of DDF. Transaction comes into a DDF classification rule. We have the dist address space. The transactions run in different enclaves because each transaction gets its own enclave. And I'm not going to get into the high performance DBATs and all that right now, but you just know that we have these different enclaves. And of course, when you're looking at these transactions in terms of response time, in terms of what kind of goal you want to give it, we are able to accumulate the CPU times, which means velocity goals as well as response time goals are valid for DDF transactions. But always understand what the transactions are doing. If you're doing a straight query to DB2, you might want to give those transactions a different response time consideration or a multiple period consideration than, let's say, if it's invoking a stored procedure. Just know that everything is accumulated back to the enclave and not to the address spaces. And that's the key point here. So for example, let's take a vanilla DDF transaction doing DB2 queries, right? So the DDF transaction comes in, gets classified according to the DDF classification rules, runs in an enclaves, calls a query. So I'm just showing two different queries here. Now let's just say theoretically what we do is we take the address space, the dist address space, and let's put it to a report class called STC DDF. Let's take the DBM1 address space and put it to a report class called STC DBM1. And let's take these two different types of transactions, and one's DDF high and one's DDF low. From a measurement point of view, we're going to get both SMF72 and SMF30 measurements. Now remember, in this discussion, we're more interested in the DDF transactions themselves. So from an SMF72, which is on a service class basis or report class basis in this particular example, we're going to get measurements for the DDF address space. And when you look at the measurements for the DDF address space from an SMF72 point of view, it's going to be very small. The dist address space doesn't do very much. It accepts the transaction, it classifies the transaction, it puts it into an enclave, blah, blah, blah. Not very interesting. And if I look at the SMF time for the DBM1 address space as it relates to these transactions, it too is very small. DBM1 does a lot of other stuff so it's going to have a lot of CPU time, but relative to these transactions, it's only a small amount of CPU time. And then you're going to see in the SMF72, because we have our report classes for the enclaves, that's where the CPU time is accumulated to, right? So because of that, that's why we can do velocity and response time goals. That's why we can do multiple period service classes, because we can accumulate the CPU and understand when we want to change periods and all that kind of stuff. Now, just to complete the discussion, if I was to look at the type 30 records, we don't get type 30 records for enclaves. What we get is just type 30 records for address spaces. So in this particular address space, when you look at those CPU times, we're going to see that the SMF30 record for DDF is where most of the CPU time is accumulated, right? So if I look at the CPU time for the DBM1, it's going to be similar to DBM1 CPU time in the SMF72. Relative to these transactions, it's not doing very much. But the CPU time of the transactions have to be accumulated to some address space. So what the operating system does, it accumulates the CPU time back to the address space that created the enclave. In this particular now, if I look at this SMF30 record for the disk, it's going to be all the CPU time of the address space as well as the transactions. And that's why we see lots of CPU time accumulated back to the dist address space. When you look at SDSF, dist always looks like it's a big consuming address space. It's not. The dist address space only accumulates a little bit of CPU. It's all the transactions that it's running, which could be at different dispatching priorities, different goals, different everything. That's why we see a lot of CPU time accumulated back to the dist address space when we look at something like SDSF. Otherwise, dist address space doesn't use up too much CPU at all. Let me see if I have another example. Here's a similar example, only it's with stored procedures. When you are invoking stored procedures, from a response time point of view, we have to understand that the response time goals might have to be a little bit longer. If we're going to have multiple periods, we need to take this into consideration, because now what's happening is we're not only issuing the queries, but we might be actually running an application in the stored procedure address space. So the response time of these transactions is going to be the entire flow, but the CPU time is going to be very similar to previously. In this particular case, if I take every one of these address spaces and put them into their own report classes, and I take the transactions and put them into their own report classes, what you're going to find is that the report classes for the dist address space, the DBM1 address space, and the SPAS address space only are a little bit of CPU time relative to these transactions. All the CPU time is that of the transactions in their report classes. But when you look at the type 30 record, again, it's the DDF address space that gets all the CPU time for all of this flow, goes back to the dist address space and not to the DBM1 and not to the SPAS address space. So that's important to understand when looking at these DDF type of transactions executing stored procedures. And then we get a little more complicated. I don't know how many people here are using the IBM web server. In this particular case, for the IBM web server, it's kind of weird the way they do it, but you have the option of turning on enclaves, or you have the option of not turning on enclaves. If you don't turn on enclaves for your iWeb, for your iWeb classification, for your Apache, IBM Apache classification, what you're going to see is your Apache address space or your IBM web server address space is just going to be a black box address space. In this particular case, we don't know anything about the transactions coming in, so you can't even give them response time goals. You can't give them durations. You can't give them anything because they're not being classified. Okay. But if you turn on classification, let's say I turn on iWeb classification, then it's very possible that we now know about these transactions. And so that means as soon as you turn on the option of using enclaves, now you're going to get all brand new transactions classified through the iWeb rules. And, we know because they're running in enclaves, we're able to give them response time goals, velocity goals, and multiple period service classes. And so you can control these. Typically, what's interesting about web server is that when they call other things, here I'm showing it calling DB2, but when they call other, let's say they call kicks, the end of the transaction is when it leaves the web server. So these are typically very short running transactions, which is why most people don't turn on the enclaves. I turn on the enclaves only because it's interesting to see how many ended transactions there were, what the CPU time of those ended transactions were. But typically, I just give them short response time goals, and I don't give them multiple periods, only because they're not really doing very much. They're usually calling other subsystems. If you have web server transactions that are calling queries and doing GWAPIs and all that other kind of stuff, then you might want to put them into multiple period service classes.
5-minute warning, Peter.
Yep, thank you. And this is just a similar example for WebSphere. For those people who are using WebSphere, you have the CB classification rules. They run in enclaves. This is very similar to the DDF store procedure type of example I showed you earlier. Everything's accumulated back to the controller region and the CPU time we know about, so we can give it response time goals, velocity goals, and multiple period service classes. And this is the same thing calling a store procedure. And the final type of transaction I want to discuss is what I call morph transactions. And a morph transaction to me is we have to understand those on our system because we have to understand what actually is being classified. And then when we look at the measurements, what is it we're actually looking at? I mean, what's happening here? So for example, here's an example where I have one transaction come into the operating system as a DDF transaction. So I have a transaction count of 1. We know that DDF transactions are eligible for response time goals, velocity goals, and multiple period service classes. Let's say this transaction goes to the store procedure address space, which also means, by the way, it's going to accumulate some queue time potentially for application environment queues. So fine, we've seen this before. And then let's say this thing calls DB2. That's fine. That all works the same. But now take the example where I have a DDF, a KIX transaction, which calls a store procedure, which calls, I think we did this one already. Actually, let me go on. This isn't the example I want to give. This is the example I want to give. I'm sorry. Let me reset myself. This is the example I want to give. That slide was there by mistakes. Take WebSphere as an example. WebSphere calls a WebSphere transaction. So this is almost like DDF calling a store procedure with DB2. And here's it doing the same thing, calling a store procedure. But let's say now we have the web server. So here's an example of a morph transaction where it comes into TCP/IP. We know nothing about the transaction. Here we go to the web server. We know nothing about the transaction because enclaves are turned off. It gets classified according to the CB rules. So one transaction comes in, all we know about is this portion of the transaction. But if we turn on the web rules, then what's happening now is you have one transaction come in, they get classified through the iWeb rules. So now we have one ended transaction. As soon as it goes to WebSphere, it gets classified a second time. This transaction ends. So this transaction's response time is typically just when it's here. And then when it goes here, it's like a second transaction. Point being is it's entering the system once, but we end up with 2 transactions. And we need to understand that from our workload manager point of view. Here's an example where I have a WebSphere call WebSphere through HTTP. Here I have one transaction comes in, runs, calls another WebSphere through HTTP. That means I now have 2 transactions. So now the response time of the first transaction is the entire flow. So I have to take that into consideration. And the response time of the second transaction is just the subflow. Now, just by chance, if you happen to be using IIOP, it changes because it doesn't get classified a second time. So in this case, the response time is the entire flow for the incoming transaction, but there is no second transaction, which means the CPU time of the entire flow is accumulated back to the control region of the first application A. The response time is that of application A, where before this transaction had the response time of everything, but the CPU time of just this portion on the left. Here's a similar example. And this is where the presentation ends. Here's an example where I have a morph transaction where the transaction comes in through iWeb. Let's say it calls WebSphere, calls a CTG for KIX. KIX then gets accumulated. We have the KIX rules here, which then calls DB2. So one transaction comes in, classified to the iWeb rules. Transaction ends and gets classified over to the WebSphere. So now I have a second transaction. The response time of this second transaction is the entire flow here, but the CPU time is just of the little bit that's in the servant region. So we have to take that into account when setting our duration. When it goes to the CTG, that's a black box address space. We know nothing about the transaction there other than the fact that it's accumulating response time, but we don't know what's accumulated there, and we don't know how much CPU time is accumulated there. When it goes to KIX, it gets classified a third time And now we know the response time of this. The kick's response time is going to be just this part of the flow, which is a subset of the entire flow. So the multiple classifications and the accounting can be very different for each. Here's just a similar example for stored procedure. And it can get quite complicated. And I'm sure all of you have this. I'm showing WebSphere as an example, but the same thing happens for GDF and things like that. But you can see here, I'm doing, I have one transaction and it includes the web server and WebSphere, the CTG, the kicks, the DB2, etc. So the point of the presentation was to kind of help you understand that there are different types of transactions in the operating system, that we just don't give it a response time goal, velocity goal, or duration. You have to kind of understand what the flow of the transaction is. Are we able to distinguish the life of the address space away from the transaction? And if so, then we're eligible for multiple periods, and then we're eligible for response time goals. So hopefully that made a little bit of sense. So was that okay? Any questions? I don't think there were any questions, no.
No, there are no questions in the chat.
Okay, so just everybody know that I hope this was useful to you. It's just a different way of thinking. I just want you to look at your transactions and think a little bit differently. Like, what is this transaction doing? Certainly go to our website, sign up for those webinars, enjoy the UK GSC conference, and you'll probably see us there in the October, November timeframe when we're in Whittleberry. So hopefully, yeah, and feel free to ask questions or send me an email. So, Donna, anything?
Great. Thank you so much, Peter. Great presentation. Looking forward to seeing you in Whittleberry. Just a reminder, this is session 5J. Please remember to submit your feedback and have a great rest of your day. Thanks, everyone.
Thank you, everybody.